Hopefully the file size not that big.
Huh?
Hopefully the file size not that big.
1080.
I put 30 FPS. I think full HD probably not like last time.
Okay, you can see
Is it clear?
should be clear.
Maybe I zoom in a bit.
Zoom in more.
Yeah.
Now it's 6:30, but we only have 35% battery. Let us wait for another 10 minutes. Have our colleagues come, then we can start formally. let us start here. Alright, so today is the second week of our mechanical design. Alright, so we want to take a look at the overview of our topic 2. Talk about the thermodynamic considerations. Assume as though thermal, right? Because later you will see our project. We don't want to actually increase temperature during generating of the pressure, air pressure, right? Later we will talk about conservation of energy and also compressor, all right? The principle of this compressor as well as psychometry of compressed air. Right? Mainly we talk about we want to filter out the water from your compressor air. So what will be what we call trouble if we have a water inside our air, right? The steam, right? So we want to avoid this from happening. We want to drain out the water. Right? Then also we talk about topic 3, pressure and temperature relief devices for pressure vessels. So this one is we want to install safety device in case of a pressure a compressor keep pumping air into the vessel. All right, then cannot be stopped in this case because of malfunction. So how to prevent this vessel from exploding? All right, so we need to install safety device. One is for the overpressure of the compressor. Another one is for a fire. In case of fire, right? If let's say fire increase temperature, how can we prevent this from happening? All right, from damaging the vessel. After that, we will focus on today the question 3, question 4, and question 5 of our project A. Because last week we did question 1, and we only have one question 2 we didn't finish is selection of the this receiver, right? We talk about the size of the receiver. Today we want to find out the receiver size, so that you are able to start your project A properly. All right. After that, we talk about the heat reclaim. The principle behind this heat reclaim such that right now seems like what happened is you power up the motor, right? Motor will turn the shaft will turn the compressor. All right. So in this case, we want to actually salvage the heat generated by this process. And after that, we are going to actually deliver this heated water to this electroplating workshop. Alright, so we want to do this for question 4. And question 5 will be this related to topic 3, the pressure relief devices. Alright, how do we actually select safety device for our air vessel? Alright, so this is what we want to do today. So chapter 2. So they actually show us the schematic of this steam turbine cycle. Alright, so what happens is, in this case, what we see here, we actually boil the water, right? So this is a steam. By using steam to turn the turbine, but what we see here, there's a heat dissipation, alright? That means the energy loss. What we do is, we only use energy, alright, 40% of energy to turn the turbine, but the rest of the 60% energy actually wasted, right? So this is what happened. So efficiency, in this case, what will be the efficiency? Only 40% doing the work, right? 60% is distributed heat. Alright, so 0.4, right, or 40% of efficiency. Alright, so in this case, it's not effective. But this is what happened because the heat cannot be controlled. After that, we have all these formula, right? If you have time, you go and take a look. And over here, this is what happened to the compressor. Alright, we talk about compressor with a piston. Okay, so the amount of, depending on the pressure, the volume will get higher the pressure, that means the smaller the volume. Right, in this case, you can see the distance traveled by the piston. So inversely proportional to the volume. So you can see the chart. Higher the pressure, the volume will be smaller, right? Then lower the pressure, volume will be greater. Alright, so this is steady flow, right? We talk about inner pipe and outer pipe. Alright, so in this case, we heat up in order to turn the turbine. This is what happened just now. We have this turbine schematic. Alright, and over here we have this compressor. Ours is a double acting piston, right? The other day we talked about our forge, right? We have seen a forge, right? So it's a double piston, double acting piston. So over here they show us is a single piston cylinder. So similar principle. Alright, and this is how the movement, right, of this single acting reciprocating air compressor. Right, so as you can see, when the piston is moving down, right, so actually create a vacuum here, such that low pressure, then the higher pressure from outside, right, will enter the cylinder, and after that, the piston will actually push in and then press out all the air. Alright, so we have we talk about the principle of this, right? Pressure and volume. So it depends on the condition. All right. Over here they actually show us isothermal. All right. Polytropic and isentropic. Our case is isothermal. We actually assume there's no temperature change after compressing of air. We want to use water cooler, right, to actually dissipate the heat. Because what happens is, if let's say there's an increase of temperature, right, after compressing of air, what will happen? We heat up, right? We heat up. Let's say temperature increase means what? Means we will have steam or water, right, in the air. This is what we don't want. That's why we want to cool down the air, right, such that there's no water inside. This is the purpose why we want to use water cooling. Right? But right now we are here isothermal. Right? So we are using this formula previously, last week. We are using this formula. Polytropic means a condition. This is ideal condition, and this is our actual fact. You will have this formula. Right? Means that you will have a temperature increase or volume changes because of temperature. Right? So this is the volume and the pressure relationship. So we talk about two-stage compression, right? So you have this chart. And this is what we do for the project, water-cooled two-stage single acting reciprocating air compressor with intercooler. Right, yes, last week. Still remember what type of cooler that we use? After cooler. Last week we discussed. You have to go back. Did you go back and do a research? I actually posted, right, after cooler and compressor this activity, right? Did you take a look? From this canvas? Right, okay, so similarly, all right, so this is to explain how to cool down using the coolant, right, to cool down this compressor air. After that, we have here is this beautiful chart, right, psychometric chart. Okay, so how do we use this because we're talking about dew point. Importantly, talk about dew point, right? Because dew point will cause water condensation. Okay, so what we are looking at here is the chart. Right now, if you go to your weather page, So what is the temperature right now? VT is 30 degrees Celsius, right? If you scroll down, you will see this relative humidity, 78%, right? If you look into your mobile phone. So how do we interpret 78%? And then you have this 30 degree, right? So right now, if let's say we draw a line, this is 30 degree, right? Then 78, 78, this is your 60, 80, right? 78, right? Nearly here, lah. So if you draw a line, all right, to 100%, then you bring down. So this one's about 24 degrees Celsius, right? If let's say now you go and buy this bubble tea, if your bubble tea is 24 degrees Celsius, you will see water droplet. Probably the gentleman. If let's say the bubble tea is 24 degrees Celsius, it will form water droplet. Dew point. Right, by looking at the chart. So right now, 30 degrees Celsius, right? You draw a line to 78%. Alright. Then you draw a horizontal line to, this is 100% line, 100%. Alright, then you draw a vertical line down, roughly, right? 24, 25 degrees Celsius. Alright, if let's say your water or your drink is about that temperature, it will cause water droplet or condensation. Right, so this is what we wouldn't want. We want to keep temperature to be very cold, such that the dew point will be very low, right? Such that there's no water form. Right, because water form will cause a problem with the compressor. Alright, so you can see probably I will try to make it bigger. Alright, so we can see this is the 30 degree, right? So you go vertically up until reach 78% relative humidity. Alright, this is the relative humidity line. Right, 30, okay, this is 78. Right, then you draw a horizontal line across, then you bring down one, so it's about 24, 25 in between. So this is a dew point, right? Dew point. So we call this superheat means now 30 minus 25, the superheat is 5 degrees, right? We call this superheat, means the energy turn this steam to water. Alright, and later we will do this heat reclaim. Right, so later we'll go through this heat reclaim for your projective. Right, so this is what happened. The objective, why we want to have this heat reclaim. Cylinder cooling to minimize the work of compression. Right, so we want to maintain temperature to be constant. Right, intercooling to minimize work of compression. After cooling to maximize condensate removal. That can be achieved in the plant room. Right, the cooling tasks are typically either done with atmospheric air or cooling water. Ours is later we will see 15 degrees Celsius. The water will enter the compressor and the cooler. Alright, so when you have time, please go to this activity to take a look at additional this information given by my team. Okay, next topic 3 will be these pressure and temperature relief devices for pressure testing. So So you can see this is a vessel. Then you have these devices to prevent overpressure of this air vessel, right? Safety devices. So they have many types, right? And over here they talk about if let's say overpressure, this one will be open circuit to prevent. And this is another type of this temperature relief valve. And you can see over here some of the valve. Alright. With the spring inside, alright, with the spring inside is a safety valve. Depending on the pressure, alright, so you will compress the spring in order to release air out. Gentlemen, don't mind, pay attention. Okay, now I want to explain this important to us. Alright, so later we want to know what is our pressure generated by our compressor. Last week we already decided. What will be the compressor that we selected? Yeah, DR4. So what will be the pressure generated by DR4? Anyone?
125.
16.3. Is that correct? A meaning is the meaning. But if you look at the table, right? You look at the table now. I show you the table. Okay, so over here we have a DR4 compressor. Maximum working pressure, alright, is 125 psi. Maximum working pressure. Right. So it's 125 psi. How to convert to Pascal? Anyone? How to convert 125 to Pascal? From your previous module. Anyone? How to convert PSI to Pascal? Alright, so just to round up, it's times 6.9 kilo Pascal. So what will be the total from PSI, 125 PSI? So equal to 862.5 kilo Pascal. Alright, so this is the maximum working pressure of our compressor. But remember, last week we talked about when does your compressor stop pumping the air?
620.
Right? Remember we talked about this. Alright, so let us take a look together.
790.
Related to what we are going to, the question we are going to do later. Alright. This one is what? 790 kPa, right? Compressor cycles off or ceases to pump if pressure rises to this level. But our maximum working pressure for our compressor is 862.5 kilopascal, right? But the design such that for safety reason, right? All right, we have to the compressor will stop pumping air at 790 kPa for safety reason. All right, this one important. Later you have to take note. After that, the next one is 690 kPa compressor cycle on for recommences to pump if pressure falls to this level. Remember, this one is 690, the pump must run, the compressor must run. 620 will be the minimum pressure in the receiver. In the receiver, correct? Means the output, right, from the air receiver must not more lower than 620 kPa. Right? Pressure in the receiver should not fall below this level for proper functioning of tools. Why? Because of the force that we have. Right? Because force require 590 as this question asks. Right? So pressure arriving at tool should not fall below this level because of the force requirement. Okay, so now we want to identify. Alright, so compressor off. At 790 kPa. So this is what we are looking at. If you have a question, please ask. If you don't ask, I assume you know. Because I cannot, really read your mind. Okay, so now we come back to this. Once we identify our maximum working pressure for our compressor, and also when our compressor off. So this is the one that we use. Alright, our compressor not supposed to work. Alright, this is maximum operate most severe. Alright, so our most severe operating pressure 790 because given by our this requirement. Okay, over here is margin 5 to 10% of your most severe operating. Right, this is your first set pressure. Alright, safety valve open at this set pressure. So let's say we take 10% from 790, right? What will be the set pressure? Because now the requirement is what? Between 5 to 10%, right? You have to set your pressure such that you install the safety valve, release pressure at this set pressure, right? So what would be the, if let's say 10% of 790, what would be the final figure? Alright, so in this case 790, 10%, right? 860. 869. This is 10%, 10%. So to make our life easy, right? To make our life easy, then we will use maximum working pressure, very close, right? 869, 862.5. Right. So in this case, we will set later on for your question. We will set, all right, pressure is 862.5 according to your maximum working pressure of your compressor. Okay.
862.5.
It's our our compressor maximum working pressure.
Oh.
So it's quite close, right? Because 10%, this is about 9.9%. As long between 5 to 10% is acceptable by the authority. This one is actually by authority, Australian standard. They actually determine 5 to 10% is considered safe because we don't want our pressure to increase to that level, right? First is 790, your compressor work. stop work. But if let's say your compressor fails, pressure keep pumping, right? So we want to make sure that the safety valve is installed such that it will release pressure at H62. Alright, very close to 10% of our set pressure. Alright, means these are 790. Alright, so this is first is your compressor failed to work. Failed to stop. Right, failed to stop. That's why it keep pumping pressure. We have to release the pressure out, right, to safe keep the air receiver. Another scenario: pressure relief when pressure rise is caused by fire. Right, another safety factor. First is your compressor failed. First scenario. Second scenario, the possibility there's a fire, right? So when fire, what happens to your air receiver? Because of temperature increase, what happens to pressure? Build up, right? So this one also dangerous, right? That's why we also have to install a safety device such that if there's a fire, we have to release the pressure. Alright, you can see over here. So it's now 790, right? Our set pressure is 862. Another 10%, 1.1. What will be the 10% of 862? What will be the value? 862.5. Yeah, about 948. About 948. Alright, about 948. If I say there's a fire, according to this guideline, 948 kilopascal, your safety valve must open to release pressure because of fire. Right, 862 is because of compressor fail. Keep pumping air, right? We want to release. But come to fire, 948. Supposed to release air, alright, for safety reasons. Cannot be exceeding 1.21, means if let's say you calculate 1.21 times your E, alright, 862, what will be the value? .5 1043, right? Alright, so now I write here fire. Right. Say 1043. Okay, so final question. This is how we design air pressure because of fire, right? Okay, and 948, we have to release. If let's say your safety device fail, right? For some very cautious, what we call supervisor, they might actually install another one, right? At 1043, below 1043, another safety device has to open, just to play safety. This is the requirement for this.
Sorry, what is P?
P is this one.
Yeah, but which value is P?
Okay, so this is your set pressure, 862, right?
Yeah.
So what we're looking at here is this one, 1.1.
Okay.
Yeah, 1.3, that means using 862 as this.
But then what is P? I mean, now you mentioned that 862 is actually PS1, right?
Correct.
Then what is P?
P.
Or we don't need to find the value at all?
Of the design pressure P.
Because now the 1.21 P, right, we need to times P.
Correct.
Yeah, but we don't know what's P.
Actually, we equate this P equal with a PS1.
Oh, so
for
we just.
project like this.
Okay.
Because depending on the designer, it can actually increase to play safe. Right? Okay, let me check. This is 790. PS1 is our 862.
I think it's the design pressure of the compressor.
Design? Oh, yeah, because we equate our design pressure with our set pressure. Right?
Design pressure.
But design pressure like that low.
Because what happened is ours very close, right? Ours very close. Because maximum pressure also quite close to our set pressure. That means design pressure and set pressure is about the same. So they're using 10% maximum, 10%. Okay, so later we are going to use this formula. Alright, this one is called Alright, so this is called the total mass flow discharge of fire safety valve. We are going to calculate the mass from the compressor air into the air vessel. At the same time, our air vessel already contained air right previously, because we know that inside the vessel minimum must have 620 right kVA right. Vessels already have air. Together we want to add one air from the compressor, let's say keep pumping, and also the air inside the vessel together. We want to calculate the mass. Why? Because we want to select safety device. We want to select fire safety device. We need to have this information. Right? The mass of the air in the tank itself. Right? Come from the compressor and also the existing air inside the air receiver. So this will be the formula we apply. Right? Later we will discuss. We will do some exercise in order to appreciate this formula. Right? So this is the project E, question 5. Question 5. But just to take note of the formula you need to use for this. Right, after that, just plug in. But in this case, YP is relieving constant, right? So equal to this. You just plug in the formula or the value into your this calculation.
Okay. No problem.
Alright, so over here they actually explain to you, right, the formula, how to use it. Alright, then we also have to use this formula, another formula that we need to use. And this is what happens is we want to convert, right? This is we are calculating the mass, right? But in order to select our safety devices, we have to convert to volume. Alright, volume flow rate. Such that we are using this formula. Alright, to convert the mass for the mass flow into the volume flow rate. Right, because according to this safety device catalog, they are using volume flow rate when they design this safety device. Alright, so they call this as a free air volume flow rate. So by using this formula, we are able to, right, to find out the volume. Okay, so let me explain again. Mass is the air mass from the compressor to the air receiver. Together with the existing air in the air receiver is a mass. Why we want to convert to the volume flow rate? Because our safety device, alright, catalog is actually indicate, alright, in volume flow. Let me show you the catalog. Okay, over here, later I will show the catalog. But the another scenario, alright, just now scenario is fire, right? Close to the air receiver. Then the last scenario here is actually over temperature protection in the event of fire, means now air receiver is actually caught by fire. Right? Three scenario. Alright, one is compressor fail. Second scenario, near fire. Third scenario is fire. Alright. So if fire means what? If let's say just now it's near the fire, right? We're scared, because of fire nearby, right? It causes temperature to increase, pressure to increase, right? Okay, now the third scenario will be fire. Means that now in fire, what will happen to your air receiver? So your steel, right? I mean your material, alright, made of this, your receiver made of steel, right? Was subject to fire. So you have to check the strength, right? The strength of your material used to make up your your air receiver. So we have to look into the design tensile strength of the steel. Alright? Design tensile strength of your steel in order to plot a chart here. Alright? So later on you will see. And then the temperature, we want to find out the temperature. This is called TR. Relieving temperature. They call this relieving temperature. Alright. Relieving means your safety device. Relieve at this temperature. We want to find out. After that, after you find out this value, using this nice diagram, then we want to plug into this formula, similar to what we have seen just now, near the fire one, right? So this one is a fire, another formula we apply, and this is the TR, the value that you plot from the chart. Plug this in, right? So this is 110,000. The previous near fire is about 10,000. Right? This is 110,000. The value change. Then we are able to find out the value. All right, find out the volume, flow rate, and then able to find proper safety devices. Okay, so this is question 5. So far, any questions regarding these safety devices? Okay, if no question, let us look into our this project B. Right, so now our focus is how to find out receiver size. Anyone already got answer for your receiver size? Can you share with us? Anyone? Take initiative to find out the receiver size. Can you share with us? So in order to find out this air receiver, right, we apply this formula, all right, from topic 1. Still remember the formula? atmosphere. Okay, so over here is our compressor. Let's say this is our receiver. Right. So remember what is the minimum requirement needed from compressor to this receiver? Right, according to our list, okay, based on this, what will be the minimum requirement needed? This one will go to the Alright, so what will be the receiver air out? The minimum requirement from the receiver, air receiver out to the workshop and the forge operation. According to the table here.
590.
No. Cannot be 590. 590 has to be
Arriving.
in the workshop.
620.
620, very good. 620 and minimum 620. Alright. So without the compressor, right, what would be your maximum pressure inside the tank? Without the running of your compressor. If let's say compressor is not running, right, what will be the maximum?
Maximum.
Without compressor running, assume, let's say compressor on at this 690, right?
Maximum will be 790.
Maximum, this one without the compressor, right? Compressor have to stop at this moment, right? Means compressor have to run to achieve 790, right? But 690, below 690, what happens to your compressor?
Start to run.
Alright, you will start to run, right? No? Compressor cycle on. So over here, without compressor, maximum is 690, right? Given by your, given by you. Okay, you see over here, they actually mentioned about 690. The question is, air receiver, compressor, okay, so this is a statement here. From this profile, it can be seen compressor normally operating with the sub pressure ranging from 620 to 700. So for the purpose of assignment, right, the volumetric efficiency can be assumed within this pressure range to be the same as the achieved 690 kV. Okay, so I need the statement. Draw a graph of receiver pressure versus time for 30 minutes for the compressor in as new state starting with the pressure at 690. and the compressor just restarted. Okay, so this is the requirement. That's why the maximum without the compressor is 690 according to our paragraph here. Okay, paragraph. So now we want to check how to apply this formula. This is a VFO, right? The maximum flow rate, that means VFO half of Q1. And this is from compressor. Alright. When forge is running, what will be the maximum you calculated last week? The demand with the forge together with the workshop. Remember, what is your value?
333.
Okay, what is your in meter cube per minute? Okay, 326, right? Equal to
Meter cube per minute is 20.01.
20 point, okay, roughly 20.01. Of course, different people, you have a different value. But 19 to 20 acceptable. Alright? Okay, so now we come to the compressor. The new compressor, remember what is the value? Your FAD, your free air delivery.
16.3.
16.3, right? Okay, so our question, another question asked is this. Assume 4%. Okay? Over here, they actually show us. Okay. Over here. When the compressor is new, it's 16.3. When the delivery capability has decayed by 4%, in this case, out of 16.3, right? What will be your value after 4% decay? 15.65, right?
Yes.
Very good. So your project, you have to show these two. One is a new value, new compressor. One is decay value. Right? Okay, now question asked is this. Which one will we use in order to actually find out the size of the receiver? Which one more appropriate?
The decay one.
Decay one, right? Very good. Decay one. Decay one, we will find out the right size for our air receiver for long-term use because we have to include these decay properties. Alright? Okay, so now BFI, we follow our decay will be. And then the maximum, right, with the force is 20. So 1 minute, right, we talk about we're using the minute here, so times 1. So this is VR yet to find out. And then our atmosphere here is 101.3 kilopascal. Alright, so P2 is what? P2 is after, this is initially when compressor enter the tank, this one is leaving the tank, right? Assume just now without compressor, alright, going up is 620, and then the one enter or initially inside the tank is 690. That's according to our question. Alright, so with this, can you find out your size of the receiver? Can you find the receiver size with this value? I hope everyone participate. You need to find out the size of your receiver in order to work out all your subsequent questions.
So, do we need to consider negative sign there?
Yes, yes.
So minus 70.
Minus 70.
No, I mean.
Because you see, this is minus, minus, also minus after that when you.
Oh, okay.
Yeah.
Okay.
So minus, minus will be plus. You must know why size is important. If your size wrong, if your size, you cannot find the right size. Later when you the project B, you have to based on your size of receiver, you need to select sheet metal in order to build your receiver. If the size wrong, that means your sheet metal use also will be wrong.
6.3 something. The answer?
It's not around 6.
Around okay. For those size around 6 is okay. 6,000 liter. Acceptable. Or 6 meters cube. Acceptable. Of course, the value varies depending on your calculation logic. Alright. But what I want is cannot deviate from this figure too much. Cannot tell me it's 2 meter cube or 2,000 liter definitely up. Or 10,000 also definitely.
6.439.
Huh?
6.439.
Or 6.139 acceptable. Please spend some effort. Try to calculate a few times to confirm no mistake. Then the value you will use for subsequent questions.
I just follow the formula.
Let us take 10 minutes. Alright, slowly do be patient, get the right size of receiver. Okay.
6.30.
6.88. 6.08 or 6.8?
I thought everybody should be get the like the same.
What will be your maximum?
PI is the volume that the 6 point something. The something that you need to find the volume.
What's the VF0 is different? Because some people VF0 is different. But you say you all have 50.01.
Yeah, because I thought they used this to calculate. Yeah, but how come like everybody get different?
How you find it? What? Why is it
The delta T he say take as 1 minute.
Cannot run away, but you're using based on this. How come different from here?
4%.
1% different.
Maths.
15.64 feet. You cannot run away.
Correct. Sir. 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 Actually, the compressor that we choose, right? Sorry.
Not DR4.
It's not the other.
The maximum requirement from everyone from workshop and the folks last week we did.
The compressor that we choose is DR4, right?
Yes.
But based on the ER model, right, it mentions that the output energy can be recovered as water, which we need for the electroplating, right? I assume. But this ER is a two-stage one, so the BR is a single-stage one. Why we are not choosing the ER model?
Okay, yeah, well, then you see the spec.
It's a bit higher. I mean, if we choose the lowest, right, which is a bit higher, is 16.3, it should be 25. So in a way,
You see
we
25, I
can
mean,
If let's say 25, you do not need a receiver. But our question asks, we want you to design a receiver. So you have an average demand need. But when it comes to search, you still have a receiver to cover. This one, because it's too powerful, we don't need to have receiver. The contractor can supply sufficient. But because our maximum 20, right, that's what you mentioned.
Yeah,
But not 25. So it's actually the cost you put in here. Alright, to me it's wasted lah.
Oh, okay. So in a way,
Yeah.
I think a receiver is cheaper. I think a receiver.
This is what they claim. But it depends on you. If let's say you are rich, then okay, you can use this. Right, but our purpose of this is want us to design the proper air receiver such that to meet the search demand.
okay.
So this is ideal design. That's why I want you to get this. Then subsequent questions related to what you actually look at.
Oh, okay.
This really like
Yeah.
follow through the flow. If I might feel like, this one minus this, right?
Yeah, correct. But you have to have times the 620 minus 690. You don't have that.
Because the other is page.
It's P2 minus P1.
I thought it's a page for page 2.
So that means without pressure you have 690, but now your demand is 620. So this is
G is good.
optimum.
I think it's gauge, pressure in gauge, KPA gauge. So it's 620 minus 690. It's the one that they given.
Because the cycle is 1 minute cycle.
So I think you just shift this up, then divided by this bracket. This one I think this one is correct already. You just divide by this. Yeah.
Got negative value. All these are in meters.
Yeah, a meter cube of yeah.
But to be honest, I yesterday do the I kept reading out.
You mean the questions?
I mean, the only 10 minutes.
Yeah.
simple cable.
I think this one we already, I think we consider we do already. This one is we use the average, then we mentioned that using the average, then we use that's why we select this compressor. Then the second one is the 4% future decay. Actually, I got two already. I mentioned here yeah, here using this model got 4% decay, then we got this FAD. Then he mentioned to give some comments and reason why we choose this. Then we say this is actually if you see the decay right after decay, the pressure is lower than I see if we decay right. Actually, if we decay, we got lower than the average. Our average is 15.93, right? But if the 4% decay is 15.6.
Is it not a percent decay?
Sorry. Okay, so our average is 15.93, right? So after the 4% decay, right, it falls below this amount. So is it still okay? I'm not very sure. Like, okay, so the average decay, right, for 4% is now 15.65. Then our average is 15.93. So it's now the 4% average is lower than our average. So by right, it shouldn't be suitable for the long run. Yeah.
Say that
14.9194.
No, this is the non-peak one. So this is our average. So average is 15.93. So just now we mentioned that we have the 4% decay, right? So 4% decay is now 15.65, which is low.
15.6. 4% decay. Yours is 16.15%.
15.9 for the average.
acceptable.
It's slightly lower.
Acceptable.
Yeah.
Why is it acceptable? Why is it acceptable?
Because about 3% to 4% different. Right? Because we're talking about the decay, right? Now it's yours about 3%.
Yeah.
Okay.
So yeah, I now I remember after I said this one, then that time I remember if the decay up to 4% is lower, then that's why I say it's slice closely to requirement. And I say therefore it's cost efficient. But he say need comment mah, so I just write something like that. For B. But then he say need to give like advice or something. I say you cannot add anything anymore. The last one I also just mentioned if they can give this performance curve or curve, then performance curve. So in a way our question do finish already.
So they said we're thinking like how do I pay? So normally working our professor is
They say it's required. 6.9 is the minimum. This one.
our one is what? Our one is 1 to 5 months. Yes, right?
Yeah.
Our compressor is 1 to 5. So our one technically is below.
No, 1 to 5 is around 860.
So our one is more. That's the maximum.
Yeah. But I mean, with this limitation, this compressor should have reached the max.
Just selected and white. So maybe I'll just put it on because it's a max, right? The max open this body I think. You see, this right? You told me to say about the fire and the cannot exceed. Because of this compression field or something. Yes? No? And see with the population. Give us what? How do you get VR? 60.3, so there's what? There's this, right? Oh, yeah, that's beautiful. 60.9. So B with the average, that's why you do VR.
Okay, anyone still don't have your air receiver calculator now? Anyone still cannot find out your receiver size? All got it right? All got it right?
No, I don't think so. Just get to know what's the size.
So our receiver size is 6,000.
6,000. Oh, 6. No, 6,000 liter.
Not question one. Question one is to find the correct. From there, this is question two. From there, we see what is the no one lah.
File size, don't think can. Let's get a file size max. He said all the lectures.
I think can.
Okay.
Can just delete.
I don't think
I see how can delete.
Okay, now you already have your receiver size. Your question wants you, alright, to actually draft out a table showing every minute. As you know, right, 5 minutes per cycle, right? Your force on for 1 minute. After that, stop, and then 4 minutes is the workshop. 1 cycle. Follow up, second cycle, force on for 1 minute, 4 minute workshop. Third cycle. Alright, so question asked 30 minutes means you have the least. And then over here you can see, alright, given 690 initially, cycle number 1. Cycle 1 new compressor, force on. Right, volume required 19.56 because why? Because force operation, right, is the maximum of the surge. So what you need to do is to calculate after 1 minute, alright, then what will be the volume inside the tank. Another minute, you calculate again. Alright, by using the formula. So you list, alright, and then you calculate. As you know, right, your tank volume cannot be lower than 620. Alright. After that, if let's say the pump keep running until 790 must stop. Right? So in this case, sometimes you will count a cycle that, okay, you can see this within 1 minute, right? Let's say about 30 seconds. Alright, so the pressure grow until 790, it will stop. Right? After that, it will bring down again the compressor off, then you will see the pressure low, lower down again until 690, it will actually run again. Alright, so this is how you are going to use this list. Mark will be given for you to actually list up every minute you calculate. So you have to do these two tables, right? One is with the new compressor, one is with the decay. 15.65. Alright, so you have to generate this list. Okay. So that's to warm up, right? You try to do the first cycle first in the class. Once you get it, because once you do 2 or 3 times, at least you get it. Then go back. When you write report, you have to provide the list. Alright, 30 minutes. Okay, and then during this cycle, right, what happened to the volume inside the receiver?
What is the volumetric?
Volumetric requirement means remember 19.56 is the workshop the maximum requirement.
don't think the volume is just like that.
Oh yeah, the one is 690. 690 is
Or is it must add up?
I think the new one. I think it's a new Excel. The new cycle with the photography.
No, but this one is really it's the same one because this one every minute the watch on off then on. So actually it's the same. I mean we can use a new table now, or we can
The new
just
table got same format but new table, but then the heading is different. Heading should be the teacher. Pressure.
this one he show like no pressure. He only got volume.
The 610. The 690. Yeah.
Okay, this from the previous class. You can see, right? They actually draft. So again, you can see, of course, the value will be different. Don't go and copy. All right? Because why? Because this is their receiver size. Your size will be different. Right? So in this case, the calculation also will be different. You cannot cut and paste this. I just want to show you. This is how you do it. All right. Every minute you will see. All right. Inside this, the value of the P2 means output. The P2 here, right? P2. All right. Will be different. And also your compressor and the forge status. All right. So first cycle forge on, followed by forge off for 4 minutes. On again, right? So if let's say your compressor below 690 have to be on. Right, below 690 have to be on. Until this part, Alright, you can see more than 790 you have to be off. Then it will slowly come down to 734. 690 again have to power on again. Alright, so this is you're going to drop this table. For this is new compressor. Right. Next one, another table will be decay by 4%. All right. So you can try out first. Try out the first cycle, 5 minutes. Get a hang of it. Then the rest you go back. Using your Excel, you can do it very fast.
How you get P1 the value? How is the P1 value up and down?
How do you get the P? Actually, how do you get the P2 value?
No, because P2 value. No, this one you have to apply the formula.
Right,
Because now you already have
P1.
your receiver size.
Okay.
You see?
Receiver size 6,000.
That's why first you must find your end receiver size. Right, then you enter the value here, you can find your whatever variable.
The T is always 1, the delta T.
Because our 1 minute cycle, 5 minute, right? 5 minute cycle, 5 minute cycle.
Per minute.
So your compressor is we are using a different one from the one that we used.
16.3 is the new one.
Okay. I thought it was.
So delta T is what? Delta T is per cycle. Delta T is per cycle, is it?
Delta T. Delta T is the time.
Time per cycle. So you say 5 minutes, you change the T to 5 minutes.
Correct.
So I times the delta.
So I don't expect everyone is 5661 because your calculation will show what is your volume size. Right? And then once this one value different, the rest also different. We don't go and copy. It means nothing. It means nothing.
16.3.
Alright, so use your value. Please do it for 5 minutes, 1 cycle. Just familiarize yourself how to apply this formula. Right? I just show you so that I can guide you, but I cannot let you copy. Okay, so we are answering these questions. Question 3, alright. Compressor is new. Also, part B or part 2, when delivery capability has decayed by 4%. Alright. Okay, let us go through this question together. Consider now the receiver ability to prevent compressor stop-start system from cycling too often. We are assuming, because if your receiver is the right size, that means you don't overstress your compressor. We are assuming for the purposes of this question that a simple on-off motor control is being used. Right, this is for the compressor. Large current flow during motor startup and too frequent also will cause motor to degrade. Right, so for a fixed size of receiver, comment on what would happen to the length of time between compressor start and stop as compressor volumetric efficiency decay due to where? 4%, right? You will see compressor keep turning on, right? Because decay, right? So you have to work harder to actually pressurize the pump, pressurize the tank. Right? Using the larger of the values of volume determined at the fixed size of receiver means just now we actually use the decay 4% to calculate your receiver size. Determine if receiver has sufficient capacity to ensure number of compressors start in an hour is no more than 10 when the compressor is new. Alright, so you have to actually calculate out whether 10 cycle, the on-off. If new one definitely won't have, won't do the 10 cycle on-off. As part of this aspect of receiver volume determination, calculate compressor on time spent and off time spent. Right? So if you know the least, that means you know when your compressor will be off and when does it turn on. Majority of the time will be on, but certain time percentage will be off. Initially, you will find helpful to consider appropriate type of mean and demand with the force peaks smoothed out. Then consider behavior with the force peaks present. Draw a graph of receiver pressure versus time for 30 minutes for compressor in the as new state starting with pressure 690. So this is what I show you the list. You have to draw on the table. That's easy for you to calculate. Alright. So with this, now it's 8 o'clock. Let us take a break. When we come back, then we will talk about the kit replacement. Alright.
So powerful. Your side is already.
This side already.
This side already. Must say you put everything aside. What's your numbers? Your student number.
Oh, my student number?
Yeah, the X and Y.
So now you want to find out from after first beginning, like you will see your V1 and V2, after that we are
the value changes. I'll tell you.
very pressurized.
So basically you take
Because it's just 690, right? First we need what is the demand, right? So it will release more air. But at the same time, now your pump is because you have
so you just fluctuate.
the demand is
So it will just fluctuate in between 690, then once it reaches 790, then go back.
Oh, you already got your receiver size. How you find people?